Okay, now we will outline steps 1, 2, and 3. So for step 1, we will be in a slightly more general setting. So remember, the goal is to make vector fields show up in the second variation. So let's say we're in a setting where we're on a Riemannian manifold M, and we have a complex value function U, and we look at the Ginzburg-Landau functional with parameter epsilon. Now take a vector field on M, look at its flow, phi sub t, evaluate the Ginzburg-Landau functional along U composed with the flow, and compute the second order derivative. Denote the result by this. We'll call this the second inner variation of the Ginzburg-Landau functional along X. Okay, and we're interested, of course, in the case where U is a solution to the Ginzburg-Landau equation, in which case this genuinely defines a quadratic form, so the notation makes sense. The following lemma clarifies the relationship between the second inner variation and the usual second variation of the Ginzburg-Landau functional. And it says that in the case where U is a solution to the equation, the second inner variation coincides with the usual second variation with respect to the derivatives of U along X. The proof is rather simple. So by a direct computation, you see that ddt at t equals 0 is really just nabla x of U, and then d squared, dt squared at t equals 0 is really just nabla x U. So consequently, if you go back to the definition and carry out the differentiation, you'll see that this is really the same as, so you first get a first variation term, and then you have a second variation term. Okay, but by our assumption, this term is 0 because U is a critical point. Okay, so that proves the lemma. And that's part 1. So we found a way to perform the variations so that vector fields show up in the second variation formula. Then we go to step 2. So we'll consider the second inner variation at uj of E epsilon j, where uj and epsilon j are obtained by negating the statement of the theorem. Now, if you actually go to the definition and carry out the derivative, you get the following long formula. So the exact form of this formula is not that important for our present purposes. But let me just point out that these terms in here that are being multiplied by the Ginzburg-Landau energy density, they resemble the terms in the second variation of the varifold a lot, except that this divergence and this sum here and this curvature term here, they're all taken over the whole manifold instead of just along your submanifold. Sorry, this should be Sn. Okay, so for this to coincide with the second variation of the limiting varifold, there has to be some correction terms, right? And this is where they come from. Okay, so to figure out what the limit is as j goes to infinity, we'll have to recall the conclusion of theorem B from part 1. So it says that, recall from theorem B of part 1. 1 over log epsilon j of the Ginzburg-Landau energy density viewed as a measure converges to the weight measure of your varifold. And secondly, I didn't state this when I described theorem B, but it's true. So it's one of the things you have to prove on your way to theorem B. So if you look at this tensor valued measures, then as j goes to infinity, it converges to a tensor valued measure. Where at each point of the support, this projects orthogonally onto the normal space to your submanifold. So Px projects onto Tx perp for x on the support. So for x on your submanifold. Okay, so over here, what I mean is in terms of local coordinates, the components of this tensor are given by just nabla EA dot of U dot nabla EB. Okay, so the AB component. All right. Let me bring this down. It's probably easier to read. Okay. So equipped with these two facts, you can go back up here. So obviously you'll use fact number 1 to pass the limits in here. Okay, and then fact number 2 is helpful for simplifying the remaining terms, because a lot of them can be viewed as pairings between tensors, where one of the tensors involved is this one. Okay, for example, this term up here can be understood as just nabla x paired with uj, tensor uj. Okay, so a lot of these terms can be viewed as tensor products between, not tensor products, tensor inner products between this thing and some other tensors. So you can use fact 2 to help you pass the limits. Now, if you actually do that and just go through another long calculation, you arrive at the following formula. So the limit as j goes to infinity of 1 over log of epsilon j. The second inner variation in the direction of x is the same as the second variation of the limiting varifold plus this mysterious error term, which is you integrate over the support of your varifold or your submanifold, this quantity. This plus that. Volume measure. where nu1, nu2 is an orthonormal basis for the normal space. Okay, so this expression is independent of the choice basis on this orthogonal complement. So it makes sense to write it like this in the integral. Okay, and a couple of remarks. First of all, this formula holds actually not just on Sn, but on closed manifolds with vanishing first Betti number. Okay. So secondly, before that, that reminds me. So in facts 1 and 2 here, of course, we use the fact that we're on Sn, and Sn has vanishing first Betti number, and that's why we only get the weight measure and not the other part in the limit. Okay, should have emphasized that. Okay, going back to this computation, the remarks. Secondly, in the case where M is a bounded domain in Rn, this formula, a formula like this, was already obtained by Le in 2015. So already obtained, and it's a similar formula by Le. Okay, in that paper, he also derived an invariant expression for these error terms. I didn't state them here because for our purposes, we don't need them. But they're very nice expressions. And using that, he actually proved that assuming the limiting variable is actually a connected smooth submanifold, then, for example, stability passes to the limit. So if the limiting variable is actually smooth, then the expressions he derived tells you how to kill this term. Okay. Okay, so that's step 2, and next we'll move to step 3. So now, going back to the case where M is Sn, we applied the conclusion of 2 to these special vector fields. Okay, and recall that their covariant derivatives are given like this. Then we can compute on these special vector fields. We're very lucky. The error terms go away. Okay, so this. I'm just writing down the error terms again. But using this formula down here, you can see immediately that they have to vanish, that this error term has to vanish. Okay, this is 0. So, let me be a little more detailed here, I guess. like this, and then plus A, and then nu2, and then minus A dot mu1. There should be subscript A's here. Okay, and this is 0 because nu1, nu2 is an orthonormal basis or normal space. Okay, but this means that the limit as j goes to infinity of 1 over log epsilon j of the second inner variation along these special vector fields coincides with the second variation of the limiting varifold along these vector fields. So this is true for all A inside of Rn plus 1. Okay, now since V is a stationary rectifiable varifold, we can use the Lawson-Simons calculation I mentioned above to find independent vector fields XA, XB, such that the following matrix is negative definite. Sorry, is negative definite. Okay, so by this and by this convergence up here, we see that for j large enough, this matrix is negative definite. That's cheating, but it's really nice to be able to do that. So this is negative definite. Okay, and that's step 3. Now from here, and the lemma that relates the second inner variation and the usual second variation, you can deduce that the UJs as critical points of the Ginzburg-Landau functional have index at least 2. And that's a contradiction because by how we started the proof, they are supposed to have index less than 2. Okay, so we've proven the theorem. Okay. So let me pause here for a few seconds and say some closing remarks. Okay, so let me go back to the statement of the theorem. So this is what we proved. In case I lost you anywhere in the process. Okay, but that's all I wanted to say in this part. So it's just to give you an outline of the proof of this result. And that ends my 3 lectures. So thank you very much for making it until the end. And thank you very much for your attention. And I hope that the results and the questions I presented in these lectures got you somewhat interested in this very interesting direction. And I look forward to talking to you in the Q&A sessions in February. So thank you again. And thanks again, Ho Drew, for all the efforts you put into organizing this event. it is really great, and I really appreciate the chance to speak here and to participate. So thank you too, and take care.